You click buy on a website, and you just sit there and watch that loading wheel spin.
Yeah, we have all been on that side of the screen.
Right. You're sitting there wondering if, the site crashed, or worse, like if your credit card just got charged 4 times in a row.
Exactly. I mean, for the user, it is incredibly annoying.
Totally. But behind the scenes, that spinning wheel represents a really complex, almost frantic race against time. So today we are doing a deep dive into a really fascinating excerpt from The Secret Life of AWS Mastering Distributed Tracing by tech writer Aaron Rose.
It's a great piece.
It really is. And our mission for this deep dive is to figure out exactly how modern engineering teams pinpoint where a user's request gets stuck inside these sprawling cloud architectures.
And crucially, how they manage to do it without losing their minds.
Right. Okay, let's unpack this. The excerpt starts with this remarkably relatable scenario. We are introduced to a software engineer named Timothy, and, well, Timothy is having a brutal afternoon.
Oh, yeah. He is staring at a monitor filled with 6 different browser tabs.
And these aren't tabs with, nice graphs or visual dashboards. They are just raw, endless walls of text.
It is a vivid picture of what we call log diving. He is deep in CloudWatch logs.
Which is essentially the raw diary of everything happening inside a cloud environment, right?
Exactly. Every single action writes a line of text with a timestamp. Now, when you are looking at one continuous process, that diary is pretty helpful. But
Timothy is looking at 6 separate diaries simultaneously.
right.
And that brings us to the architecture itself, because these 6 tabs represent entirely different components of a single checkout process.
Yep. Let's break those down.
Okay, so he has one tab open for the API gateway, which basically acts as the front door receiving the user's initial request.
Right. Then he has another tab for a checkout Lambda function. That's the on-demand compute engine running the actual checkout math.
Gotcha. A third tab is an Amazon SQS queue, which is essentially a waiting room where data sits before moving on.
And a fourth tab is the inventory Lambda function, the back-end worker that actually updates the stock levels.
So he is frantically switching between all these tabs because a user submitted a support ticket stating their checkout process took 14 seconds to complete.
Which is an eternity. 14 seconds in modern e-commerce is catastrophic.
Yeah, the industry standard metric suggests that a delay of even 3 seconds leads to a massive spike in abandoned shopping carts.
So 14 seconds usually means the user just closed the browser entirely.
So Timothy is trying to manually match up the timestamps. He's looking at like a millisecond value in tab 1.
Then clicking over to tab 3.
Squinting in the screen, yeah. Hoping to find a matching timestamp to figure out which of these isolated systems actually caused the delay.
It sounds like searching for a needle in a haystack.
Except the haystack is constantly growing while you search.
What's fascinating here is Margaret, a senior colleague who pulls up a chair to help, points out this brilliant architectural paradox.
Right, because Timothy is actually a highly skilled engineer.
Exactly. He built this entire system over the past year using about 50 different architectural components. And he decoupled them perfectly using event-driven patterns.
According to every modern cloud architecture best practice, he did everything flawlessly.
But that flawless modern design is the exact root cause of his current nightmare.
It's wild. The decoupling is a total double-edged sword. I mean, we spent the last decade moving away from the old monolithic architecture.
Right, where an entire application lived on one massive server and wrote to one single sequential log file.
We broke things apart so they could scale independently.
But we traded visibility for scalability.
Right.
In a decoupled microservices architecture, a single user request, like clicking that buy button, no longer travels in a neat, orderly line down a single server process.
It shatters.
Exactly. It bounces across multiple independent compute environments. It hits that API gateway, which fires off a function, which drops a message in a queue, which wakes up another completely separate function.
And those environments share no memory.
None. They have no awareness of each other's existence.
So trying to manually match timestamps across decentralized systems like that is just fundamentally unreliable. For you listening, imagine trying to synchronize watches across half a dozen runners in a relay race.
Who are all blindfolded.
Yes, blindfolded and running in completely different cities. The text-based output of CloudWatch logs tells you exactly what happened in one specific runner's lane.
But it tells you absolutely nothing about the chronological relationship between the runners.
It is a guaranteed path to engineering burnout. You end up with these highly distributed systems, but your debugging mindset is still stuck in the era of single-server applications.
You need a paradigm shift in how you observe the system.
Here's where it gets really interesting. Margaret introduces a completely different approach. She pulls up the AWS Management Console and introduces the concept of distributed tracing.
Specifically using a tool called AWS X-ray.
Right, and the fundamental idea here is to stop treating every step of the process as an isolated event and start treating the entire journey as one single trackable entity.
To achieve that, the system has to assign a unique identifier to the user's request the very millisecond it enters the cloud environment.
And crucially, that specific identifier must then be carried forward intact across every single downstream service that interacts with the request.
I like to think of it like handing the user's request a VIP wristband at the door of a nightclub.
Oh, that's a perfect analogy. Every single room that request enters, the bouncer at the door has to check and log that exact same wristband.
It holds up perfectly. In the mechanics of AWS X-ray, this VIP wristband is known as a trace ID. When the user's HTTP request first hits the entry point,
Which in Timothy's architecture is the API gateway.
right, X-ray generates a unique tracking string. The technical implementation is actually a standard HTTP header. The system creates a header called xamz on traceid.
Okay, so the API gateway stamps the request with this xamz on traceid and passes it to the next stop, the checkout lambda function.
Correct.
Now, my initial thought was that the function simply writes that ID into its log file, but the process is far more active than just passive logging, right?
Yes, the active process is called trace propagation. When that checkout lambda function finishes its calculation and needs to hand the baton to the Amazon SQS queue, it cannot just throw the data over the wall.
Because the queue wouldn't know the trace ID.
Exactly. So the AWS Software Development Kit, or SDK, automatically intervenes. It takes that exact xamz traceid and embeds it directly into the message metadata before sending it to the queue.
So the tracking number becomes part of the payload itself.
You got it.
The beauty is that the developer does not have to remember to manually code that handoff. The SDK manages the VIP wristband entirely in the background.
And then, when the downstream inventory lambda function pulls the message out of the queue, it reaches into the metadata, extracts the trace ID, and continues the chain.
This creates a continuous reporting loop. Every single independent service uses that one shared ID to report its status back to the centralized X-ray API.
They all signal the mothership independently. The API gateway reports it held the VIP for 50 milliseconds. The queue reports it held the VIP for 2 seconds. The inventory function reports its execution time.
They are all supplying fragmented pieces of a unified story. And that unified story leads to the ultimate visual payoff. Margaret shows Timothy the primary feature of AWS X-ray.
The service map.
Yes, the service map. Timothy goes from staring at 6 tabs of chaotic, disconnected text to looking at a fully interactive visual diagram of his architecture.
It redefines observability. X-ray takes all of those individual reports tied to the trace ID, aggregates them, and actually draws the system.
Every AWS service becomes a visual node on your screen, and the lines connecting them represent the actual flow of data.
A crucial detail we need to highlight for you listening. This map is generated entirely based on literal network traffic.
Right. It is not a static whiteboard drawing created by a software architect 6 months prior.
There is zero guessing. The system draws the map based on the actual packets of data moving between the services in real time.
The distinction between designed architecture and actual architecture is paramount.
As systems evolve, code is patched, and workarounds are implemented. The reality of how a system communicates quickly diverges from the original documentation.
But the service map provides the undeniable mathematical truth of the environment.
Let's bring this back to the 14-second checkout mystery. Timothy and Margaret are looking at this interactive service map. Instantly, the bottleneck becomes obvious.
The node representing the checkout database is colored green, indicating fast, successful queries. But the node for the inventory database is outlined in red.
And the line connecting to it shows a severe latency metric.
The map explicitly displays the average response time for that specific inventory database connection. It shows a delay of 12 seconds.
12 seconds out of the total 14-second delay, identified purely visually.
The best part is the workflow that follows. Timothy does not need to switch back to a text log to find the slow query.
He simply clicks on the red node directly on the service map.
And the console reveals the exact SQL query causing the holdup. A debugging task that would have traditionally required hours of grueling cross-referencing was completed in less than 60 seconds.
This raises an important question. It sounds like an incredible capability. But in engineering, extreme visibility usually comes with extreme overhead.
That's true.
If an architecture is generating unique trace IDs for every single user request, actively propagating them across dozens of service boundaries, and constantly pinging a central API to draw real-time interactive maps, the implications seem massive.
The immediate concerns are the sheer cost of the AWS bill and the engineering effort required to rewrite the code base to support this.
I had the same hesitation initially. Recording the telemetry of millions of requests per day sounds financially ruinous.
But X-Ray utilizes a really clever cost management strategy called sampling rules.
Sampling is the underlying mechanism that makes distributed tracing viable at enterprise scale. By default, X-Ray is configured to be highly selective about what it records.
Right. The default configuration records only the very first request of each second.
And then it records just 5% of any additional requests that occur within that same second.
This is a foundational concept in telemetry. You simply do not need to record a full end-to-end trace for every single one of your 10,000 successful lightning-fast checkouts to know that the system is functioning correctly.
You only need a statistically significant sample. That one request per second, combined with the 5% variable, provides ample data to identify latency bottlenecks, map out the service architecture, and spot error trends.
All without forcing the organization to pay for the storage and processing of millions of identical healthy transactions.
You capture the insight without capturing the bloat.
That perfectly solves the budget concern. But what about Timothy's other likely fear? The implementation. Does a team have to tear their application down to the studs to start passing these headers around?
The barrier to entry is remarkably low. For fully managed AWS services, such as the API gateway or step functions, enabling X-Ray is literally a configuration toggle in the management console. You just check a box to turn on active tracing.
For the custom business logic, like Timothy's Lambda functions, I imagine there is some code modification required.
There is, but it is highly abstracted. The engineers import the AWS X-Ray SDK into their application.
And then what?
Once imported, they add a few lines of code to wrap their existing AWS SDK clients. Once that wrapper is in place, the X-Ray SDK automatically intercepts all downstream HTTP requests and database calls to inject the XNZin tracehead header.
So the developer continues writing standard database queries, and the SDK silently slips the tracking wristband onto the payload as it leaves the function.
The abstraction allows the engineers to focus on the business logic rather than the plumbing of the tracing system.
That makes a lot of sense. But there is one final feature Margaret demonstrates that elevates this beyond just a debugging tool. It revolves around a feature called annotations.
Annotations are where distributed tracing transitions from a purely technical diagnostic tool into a powerful business intelligence asset.
In a baseline setup, a trace ID tells you how long a request took and where it went. Annotations allow you to append custom business-specific context to that technical journey.
They are essentially custom key-value pairs attached to the trace data.
Right. A prime example provided in the source is configuring an annotation for customer tier with a value of premium.
The implications of that capability are profound when you consider how engineering teams triage issues.
I really want you to visualize this scenario. You have your global service map displaying all the traffic, latency, and error rates across your entire architecture. Without annotations, you are looking at an aggregate of every user's experience.
But by using an annotation, you can apply a filter in the console to strictly display traces where the customer tier is equal to premium.
Suddenly, the visual map dynamically recalculates. You are no longer viewing the general health of the system. You are looking exclusively at the performance your highest-paying enterprise clients are experiencing.
This enables organizations to prioritize their technical debt and incident response based on tangible business impact.
Because a general bottleneck causing a 2-second delay for users on a free tier might be logged as a low-priority ticket to be addressed next quarter.
But if filtering by the annotation reveals a red node causing database timeouts specifically for users generating the majority of the company's revenue,
that becomes an immediate drop everything priority.
It bridges the historical gap between raw compute metrics and actual customer experience.
It provides total context. For Timothy, it means the days of keeping 6 browser tabs of isolated text logs open are over. He opens the code repository for the inventory service, optimizes the specific SQL query X-ray highlighted, and pushes the fix.
He moves from being blind to the system's chronological flow to having a complete end-to-end view of the reality of his architecture.
So what does this all mean?
It represents a fundamental maturation in how the software industry handles complex architectures.
To summarize our journey through this deep dive, the transition to microservices solved our scaling problems but broke our traditional methods of observation.
Distributed tracing, through tools like AWS X-ray, rebuilds that visibility.
It takes us from a disjointed, text-based log hunt into an interconnected, real-time visual map. It empowers teams to pinpoint latency and errors instantly without manual guesswork.
If we connect this to the bigger picture, the tools we use must evolve alongside the architectures we build.
Definitely.
For years, the industry was heavily focused on the mechanics of breaking massive monolithic applications apart into highly scalable, decoupled microservices.
We succeeded in that, but the resultant loss of operational visibility was severe.
Distributed tracing is the industry's course correction. It asserts a new standard. In modern software engineering, having deep, interconnected visibility into how your system operates in real time is just as critical as the code written to run the system.
Because an architecture that you cannot observe is an architecture you cannot secure, optimize, or maintain. That brings us to a final thought for you to carry forward. Because distributed tracing maps your environment based on the actual network traffic, rather than how you or your team think it was designed.
What unseen bottlenecks, forgotten API calls, or surprising architectural truths might you discover hiding in your own systems when you finally turn the lights on?
It is an inherently disruptive question. The map is not the territory until you finally force the territory to draw the map for you.
Well said.
That is all the time we have for today's exploration. Keep analyzing your systems, keep questioning your architecture, and we will catch you on the next deep dive.